actually 2 o'clock, so I think we really should quite make a start. So can I welcome everybody this afternoon? I apologise for my voice having decided it's going to part company from me again today. I have actually had it around for a couple of weeks, but it's disappeared off again, which is unfortunate, but sorry to give you the gravel voice. Really nice to see so many of you joining us. For those of you who are not terribly familiar with some of the faces that are bobbing around on the screens at the moment, there are a lot of people, as you will recognise, who know each other, and that's one of the wonderful things about fellowship from SEGH, is being able to share that that networking and people who've known each other for quite some length of time wanting to work together. Without further ado, I'm going to hand over because I think you don't really want to hear from me, you really want to hear from our speaker. Our speaker is very well known to us at SEGH, but also well known beyond that as well, and has done an enormous amount of work in the field of environment and geochemistry and health. So really looking forward to hearing this afternoon's talk. Can I hand over at this particular point, if we don't mind, Xiang-dong?
Thank you, Gillian, for the introduction. I will try to share my screen right now. Can you see from there?
Yes, thank you.
Okay, super. And I thinking I would thank you very much and for Gillian and Oliver to organize this fellowship like talk. And so I would probably very much like back to home actually. And so one of the early, I would say the earliest kind of a professional society I joined for SEGH. And I joined the first meeting, I believe is 1990. That's almost about 32 years ago. So it's still like SEGH is a kind of like my academic home as well. So I want to just, because it's probably have our young like members to join in. So I would just quickly introduce my academic journey and over the last 30 years. So this particular, using some of the slides, I actually for about this kind of Golden Smith geochemical conference back in July, which actually I'm very lucky enough, I thinking probably representative for our society to getting this year's Clark Patterson Award. I believe quite a number of us know Patterson's work, which actually two of the most distinguished part. You can see for about this silver metal type, which he actually measures the age of the whole Earth, which 40.6 billion years ago. And from this data in 1950s, by now, where it's almost unchanged. That's really consider how about our geochemical tools have improved. The second part, probably more familiar with our environmental geochemist, is his early work on the lead in gasoline type. And so, which actually for about a wide range of lead contamination in the environment. Okay, so I just want to put in my current name card issue for you to know. So I thinking anyway, I skip all this kind of a title or other posts. I'd be very proud to see this about the fellowship, like talk as SEGH. I still be treated my home base. So anyway, and I thinking probably just give our young colleague or a new friends a bit of a quick introduction. So here is my 3 major kind of like a research area regarding our geochemical tools for assessing regional pollution. So that's probably my early work within the UK for a PhD study. or like early work when I'm back to Hong Kong for about the regional Pearl River Delta type of study. So we also have our urban geochemistry of the pollutant, and both for metals and for organic. And also probably last kind of like a decade, we focus about PM2.5 and some of this microbial like study is major related for environmental health. I'm just using a few slides, particularly for our young members to know my academic research path. I just want to joking is I'm using my dad liquor cups for very early like a chemical experiment, and so I have hidden some of this like the cover where I cannot wash out the color. So then in high school, I thinking there's enjoy like a chemical experiment, and we have produced these hydrogen balloons using kind of a strong acid with metal. So by that time, you can see about when the splash of the acid, I have a holes in my pant, but not as fashionable as now. You have a gene in your hole, you can be, my mom found out that can be a big problem. So I thinking like I would join very fortunately for one of these were funded like Earth Science Department in Nanjing University. I remember whereas my high school teachers mentioned, you go, I have just taking my major as chemistry. So he said like you actually entered in geochemistry, this advanced branch of chemistry. I still remember that it can be true. So that's kind of like a really interesting years. And I just want to see, particularly in our senior year as undergraduate study, or about early few years for master degree. And here is the journal. I remember we have taken as case study. So GCA, chemical geology and applied geochemistry. I haven't, by that time, for our year, environmental geochemistry and health. But anyway, I really fortunately have a scholarship where just landed me at Imperial College in London, where by that time we have a very large group consider about environmental geochemistry. So here is actually belong to the Royal School of Mine. The red brick building is the Royal School of Music. So I very much own some of my early research to Professor In Sangten's, by that time, my PhD supervisor, and some of you, if you're searching about this very classical kind of reference textbook type, is applied environmental geochemistry, which is added by Professor Sangten, which actually have very much on the early work. So I started my PhD project where you can still see the title of my first page, study multi-element association in a soil plant system in some old mining area in the UK. So that's kind of my almost the first paper in our environmental geochemistry in the house, which have on this antimony and bismuth in soil and pasture herbage. So then about some of further work considered with applied geochemistry for its soil plant in the old mining area. And then some of further work on the chemical geology and consider with other kind of like geochemical like analysis. Okay, so after a PhD and a short period of 1 year as postdoc research, I think by that time, we have a co-work with Atikos and for some of these soil sample from Greece. So that's a very interesting kind of like work from there. So I landed one of a job, which actually for one of the environment consultancy, environment resource management, ERM. So the next years, I was back to academic again after about a very interesting and fully engaged environment consulting work. So here is the Hong Kong Polytechnic University campus. So our lab is somewhere here. You can see from the building there, and hope very much some of our members can visit us when the international travel can be much relaxed. Okay, so that's like a very quick few minutes. I want to just to give our like new friends or some of our young members like the career path I have. Now back to the particular topic today. I would like to want to ask our environmental geochemist. We still have a big role to play. I want to setting about the big skin and sense for our environmental geochemistry field. So definitely is one of these like everyone well-known term. Anthropocene time, we have this planetary boundary. We have the concept of one health, which actually consider for the human health, animal health, and environmental health. Anyway, I would quickly touch a bit for this Anthropocene one, which I believe for our geochemistry, particular earth science like community, this were accepted like a concept, and which we already have a very solid evidence for about this particular human activities change the natural environment. So we can see that globally there's a steadily increased human influence on the planet Earth, which really starting from the about the Industrial Revolution, which back to the 19th century. So a new geological like term we are using now is Anthropocene, which actually proposed not very long ago. So only probably about 20 years ago by the Nobel Prize laureate and Professor Paul Cruzen in recognize this dramatic like change. So in doing that, we still haven't like really well recognized how is our starting for the Anthropocene and still under debate. So we are using about Industrial Revolution back to the 19th century, or we're using probably about starting 1950s, because that's after World War II, there's a great like acceleration of whatever about this socioeconomic development, or from about this Earth system like trend, including we're talking about climate change, or consider within other kind of environmental issue we are facing right now. Okay, I think I do not need probably about our kind of a world actually prepare for next month's sustainable development conference. I thinking that's probably which we are facing the really a challenge ahead for about coordination for various countries on this kind of really a global like issue here. But I just want to pick up if we are looking about sin number 2, which actually touch about this planetary boundary, which there's kind of like a few issue particular relevant to our environmental geochemical society. So for example, there's a novel entity in place for some of these chemical pollution issues. We have about consider is a different chemical form, emerging chemicals of concern, and a particular form considered with nanoparticles, considered with a fine particle matter. We're going to talking about today on the air particulate matter PM 2.5, or we can do a little bit for my talk today also considered is antimicrobial resistant. We have from about health perspective, from about environmental perspective as well. We can also have a little bit for about our using example about how our toxic mixture and multiple stress So we are not actually majorly for the environmental exposure. It's not only for about one single chemical or one single stress. It's coming from quite a number of combined issues as well. So I'm thinking that's give us our environmental geochemistry can be play a very active role in identify what we call about this novel entity, consider about quantify their operation space, and the manager about this planetary boundaries from we can contribute to the society and the world development. Okay, I quickly consider to move on to our air particulate matter pollution. So if we're going to consider any of environmental problem facing the current world, probably you can actually from the WHO's list, air pollution particular is a #1 issue, because you can see here, we have every year around about 7 million premature deaths. Consider about they cannot reach to the full life expectation as healthy individual. So that's quite a number of this kind of different region consider about this causing by this air pollution problem. So because last year, 2021, so World Health Organization have lowered its air quality guideline to 5 microgram of cubic meter. So if this one was really actually imposed because it's guideline rather than legislative limit, we have over about in the world 90% of the world population living in an area which cannot meet the WHO air quality guideline for PM2.5. That's really an issue. So I think in a way you can compare about really air quality good day compare with pollution absolute day. I thinking also most of us are close familiar with what we mean by PM2.5 on the size and the inhalation risk. Okay, I think probably we are lucky enough, particularly compare most of the region in China. Hong Kong is actually can be enjoy a better air quality, but this still and some of the days we facing about really air pollution absolute. You can see about this some of certain are listing on this pollution day. So the air PM can reach to be 119 milligram per cubic meter. That's really significantly health advice for sensitive populations. So with that in mind, we can see there are many of way like a research community and whatever from environmental chemistry, from toxicology, or from other like air modeling, from public health profession. There are many of the study because the air quality involve quite a number of disciplines. From about we can see from emission source into the PM mixture, consider within dynamic like atmospheric process, and consider about how reach to about these large populations causing about these health issues, even a short-term acute effect, consider with a long-term like chronic impact effect. So this particular issue, both for PM2.5, why it is complex? Because there's a kind of a different source contribution. Because there's a size difference for about both for the chemical and the microbial component, but also have a consider about the fine particle can enter our respiratory tract, which actually can affecting quite a number of our healthy problem. So in other words, if we're going to see the particle size and so the component, you probably can see about this the different like PM2.5 when we mean about any of the dynamic meters is less than 2.5 micrometers below. So there is also have a kind of like the very fine particle, which consider within even for about smaller than the bacteria, and it can be even about on the same side as virus. So in this particular part on the left-hand side, we majorly consider with a mineral composition, and which actually is a strong point for our geochemistry to play a role. So in the right-hand side, we do have quite a number of these microbial, from about large spores, consider with bacteria, consider virus, even consider about a very basic like proteins and molecule. So consider all this, another big issue is within kind of like PM2.5, many of the very fine particles can actually have their different chemical composition. So either about there's as well known about heavy metals, and there also can have a kind of like the pH organic component, consider within about a smoke and whatever black and brown carbon, consider also within about this gas pollutant as well, ozones, SO2, and nitrogen oxide. So they also have quite a different composition. You can see about there's from a seasonal variation in winter, because in north part of China, where like coal burning for the central heating is still about this common need. But in the southern part of China, although there's not as significantly seasonal pattern, but they still actually have about the different chemical compositions. So in one of our probably early work is we have about analyze like this was the diagram of the generated from WHO's own official data. For one example, we have a plotting each of the country and the regions, the annual average like PM2.5 pollution level. In other side, we have a putting about PM2.5 related deaths, which report in certain amount of this annual PM2.5. You can see there is a wider gap range. So even from the low like concentration, only 20 microgram per cubic meters. So you can see there's a low end can be very much like whatever in a very kind of economic developed country, whatever UK or US here. But there are even lower, there are some of the countries actually have a high PM2.5 related deaths, like mortality, and very really high. So, but there are also consider some of the extremely high level for the annual. This is not a single sample. This is for the annual PM2.5 concentration. Their death rate may not actually large or high. For example, taking example like Bahrain or Qatar, they have a high concentration PM2.5, but like the health PM2.5 related deaths, it's not very high. Because anyway, that's one of our high purposes. This PM2.5 contribution from this natural sand from Sahara desert, rather than from about this whatever this chemical pollution from whatever industry and vehicle emission or other kind of coal burning and other process. Anyway, we from our comment published in Nature, which about 4 years ago. So we want to propose one of this kind of this concept is equal amount concentration, not necessarily equal toxicity and potency. So that's what we're going to prove to see how about from our geochemical point of view, the chemical composition and rather than the dose play about the key role. So that's why leading to our next one. So how about this iceberg modeling? Because we all know about PM2.5 is really a chemical mixture. So in that case, we have probably if our various analytical tools, we can analyze up to 10,000 different chemicals. In PM2.5, we can collect it for about whatever 4 or 8 hours. But here, I'm thinking what we want to put in doing about quantitatively for the toxicity analysis is on the right-hand side, we have using about the chemical analysis, which every us was quite familiar with, heavy metals and pH countages, and then we're going to have about the concentration of the chemicals. So the concentration chemical, we can compare how toxic each individual known chemicals. Then we can put in about effect potency of each of the chemical. Then putting as about combination of the PM2.5, they have to be on a mixture toxicity. So in other one, and we do have a kind of around about 50 different metals come about from 30 different kinds of pH. So they have a mixture toxicity prediction to be on a validated about concentration addition. So each of the single individual compounds or individual metals can plot together to making about unified combined PM mixture. So in other way, how we can do it, we can using a bioanalytical assessment, consider with a biological effect of the total PM2.5 we obtained from the field sampling. We're going to see how much each of the effect can be explained by the different analyte metal concentration or different there's chemical partitioning. So the mixture toxicity of known of the metals, whatever combined or individually, or the pH counter can really give us a quantitative contribution to the overall toxicity. And definitely we can using a cell as one of the indication here. So I just want to give you one example of just skip about the technical detail. You can see this quite a number of the metal are listed here. Also consider with a particular about some of the pH countages we have. So in this part about that, I would just ignore about this ECIR 1.5 is you can just taking as a toxicity potency. You can see if we are putting there can be about 5 order of magnitude of difference. So in other way, so if you have about a sample from whatever from London, compare from Hong Kong, or compare anywhere from Jerusalem, and you could have a quite a different, even on the same total amount of PM2.5. So their toxicity can be very significantly. So I just wanted you to put in about span really about this kind of different. But how we, just as we mentioned, how we actually assess each of these component, metals or pH compounds, compare within real issues. So we can use one we call it like a chemical edit predictor model, compare about our totally mixture, the real field collected like compounds. To if these two, the balance are equals, we can actually using the chemical addition way to subcontract about this individual contribution to make it more kind of like a really quantitative data here. Okay, that's kind of like the general principle we can do on this one. I just skip about other technical data. I'll give you some of the result for as examples here. So for example, if we are taking about a PM2.5 sample in Beijing, a more polluted, compared with the southern city in Guangzhou. So you can see the total metal contribute around about 11% in Beijing, which actually contribute towards about 7.3% of total toxicity in a cell where we can testing from about PM2.5 really field collect sample. But if we further using about chemical active approach, we can even quantify who are the major player. You can see here, iron, copper, and manganese are much more than our normally regarded for lead or chromium and zinc. So that's really interesting, kind of the first evidence and a solid kind of data to see not only for the concentration, but how concentration chemical form really contribute towards the overall toxicity, towards about testing cell. So anyway, you can see quite a different type. In a same way, we move on for the organic compounds. In this particular case, we're using pH as example. For example, about in Beijing, because it's a coal burning, so they have on 27% from contribute from this various about 10 different, 12 different like pH compounds. But in a southern city, Guangzhou, about 17%. So, but even more striking is the two benzone peride or dibenzone peride, two compounds actually contribute over 90% of all the pH. So this actually consider about this combustion source. So in other words, if we are taking these two compounds away from the two total PM2.5, we may actually reduce the toxicity or health impact about 20%. But these two compounds concentration-wise is very, very much a lower concentration. So that's why, so the concept first proved these two predominant driver for toxicity for the whole pH compounds we have analyzed in PM2.5 field collected samples. Okay, then I just wanted to put it that way is, so after analysis, even for about this the last slides, we can only quantify about 30 or at most about 40% of the total cell toxicity. What is the rest? So in other words, can we actually for this like 60, 70% unknown? That's leading my next topic. What about other ways? So in this particular case, we have leading us to thinking other non-target compounds or even about less focused microbial compounds. So in one of the particular case, we are testing this endotoxin. It's a combination from a microbial bacteria and a virus type. You can see the green part. They contribute significantly compared with metal and organic. I must say is we have changed a little bit for the city because the Beijing sample will run out for the first analysis, but we continue to collecting this another city in Nanjing, and compared with Guangzhou, we still have a sample to run. So that's about the way leading us to really taking care. PM2.5 not only by heavy metals or even organic pH, so they also we need to taking care about this bacteria and whatever possible, even free DA and virus type proportion. Anyway, that's a common issues, but not very characterized or studied. So here we have about this biological origin under the electrical microscope. They can contribute towards about pathogen. They can also towards about allergen like a component as well. So one of I just want to highlight we have putting about one of our recent paper published about only 2 weeks ago is we have about this airborne microbial like full pictures in a global significance. So where you can see about there's quite a different. We have collecting almost 70 different sites along the globe by our own analysis. We also compile about literature data to putting them into a whole database. Then we can calculate about this one of group 1 is majorly considered with human and animal associated environment. They have their characteristic for airborne like bacteria. Then come over number 2 is majorly considered about this kind of terrestrial type on the soil and the rhizosphere like microbial. Then for the deep ocean, we have about quite a different oceanic study. So if you compare about their composition in orange, you can see about the blue ocean, definitely there's a kind of a environmental one is by this ocean itself. But for the terrestrial background, majorly for this plant is the key issue here. But for the urban area, we have the most complex, almost every single source can contribute towards it. Another interesting point is if we plotting the latitude towards about this whole richness or for the bacteria abundance and the relative kind of a diversity, biodiversity, you can see actually these airborne genes majorly in the middle latitude, particularly within about temperate regions, rather than about our kind of the major biological species. Subtropical is the most diversified, most abundant populations. But that's in a line within our global study for ocean and also with the soil microbiome as well. Okay, further away, I just want to, I need to take care of my time.
I was just about to say, we're actually 40 minutes in. I'm very happy for you to carry on if this wraps things up nicely, but equally, if we want to give chance for questions, I'll leave you to decide whether or not you want to wrap it up quickly.
Sure. Okay, I skip some of the detail anyway. So for this, I just want to highlight there's kind of a urban and background difference considered with urbanization, including some increase the non-biological particle and some of other component. So they actually have about less filter like our natural environmental ecosystem work. Okay, just putting about one case, if we see some of airborne microbial compared with the marine and topsoil one, we can see how about the human impact issues. For that particular part, we can see the source contribution contributed significantly, and consider within kind of the climate condition contribute another 25%. The air quality contribute around about 30%. So that's how about this really give us the first hand about the data considered with airborne bacteria and how this contribution towards this kind of PM 2.5 toxicity and health issue. I touch it very quick. So putting about this bacteria on a map, we can see how about our related environmental health issue. So most relevant one, if we're digging about this particular medical relevant one, we have the lower respiratory infection, LIRI, can be really connected to about this both the chemical stress and both more importantly the microbial component in the air particle inhabiting, including quite different even the virus. We currently have the pandemic for COVID-19 different virus, even the bacteria or even large particle and fungus as well. Anyway, and I just wanted to putting on one of the issue is, although we have really making significant progress for this LRI, the infection on global number, but we still have this in the middle way of pneumonia type of the virus still persistent to be a major dominant for particular for young children's health issue here. So putting that away, I just want to highlight another dimension we have been working on is about antimicrobial resistance. We all know about this penicillin was invented almost about 100 years ago, but putting about in optimal use during the World War II, and we have the golden age. But there's a kind of like after only about 20 years after this wide use, we have considered about antibiotic resistant plasmid. So in other words, some of the antibiotic cannot be effective, and because the bacteria have acquired some of the resistance. So that's leaving quite a significantly health issues we need to deal with. You can see the many of community and hospital acquired case. I just want to list here, which actually can be very much on the different environmental medium through ingestion, contact, inhalation for about the skin contact as well. So then just putting our way, still we are sticking on the Air PM because airborne resistance can be a really big issues. So I just want you to compare using this one. For example, for the natural environment, how many of antibiotic resistant genes compare about totally gene number. So you can see about a lower end for the natural environment compared with engineering system, including about our wastewater and landfill side, compared with human and animal like fecal samples. But you can compare a PM2.5 and inhalation condensate. It's really have about high range of this kind of antibiotic resistance. And so in the past, we largely ignored for the airborne like a bacteria or airborne virus kind, but they can really have our inhalation like a health risk. Anyway, there are many of the way which we're going to analyze from the source into air transport model into the final consider with health issues for both about infection and colonization, and finally into about the different human like body part and causing about health problem. So in doing this, we first analyze as our geochemist. We always starting from source and the pathway and then environment fit. So in doing this, we have analyzed one of these wastewater treatment plant in Hong Kong, and then we contribute how much the airborne transmissions from this aerosolization process and how they are contribute towards the source tracker to really understanding their way. Interestingly, they can only contribute from the wastewater treatment plant about probably about 20% of bacteria count, but they can contribute over about 50% of the all ARGs we have through in the ambient air in the urban area. That's really a staggering kind of facts. Another way is how our medical setting, like in a large hospital, and how there's finally from this air conditioning system, air circulation system, we have putting our like high volume PM2.5 sampler here. Then we can see really these antibiotic resistant bacteria are more abundant from our like side as this in patient like a building compared with about this wide ambient urban side, which actually they have about the characteristic from the medical use of antibiotic and ARG pattern. Okay, I think I need to skip some of the debate we have considered within about COVID-19 we are facing now, about the droplet and the airborne transport, consider about the particle size which its carry on. Also, another way is we further analyze not only for about bacteria associated ARG, but there could be bacteria and phage, the parasite of bacteria, and also a free available like a DNA part in airborne as well. Okay, thinking I almost try to wrap up about the talk now. So we can see there's a potential interaction. In one hand is our familiar geochemistry work, physicochemical aging. We have the heavy metal, we have pH, we have different like smoke and gas phase. And then they all can cause about oxidative like damage, DNA damage, stress, and other kind of dysfunctions. And the other side, we do have this kind of a pathogenic microbial like agent, whatever about influenza, SARS, and other kind of pathogens, which can cause about health disease. Consider about inflammation in our body or in our system. How about these two really work out for about assessing the overall environmental stress for PM, both for the chemical composition and for microbial like agent as well. So I thinking I particular just highlighted the paper we have on the environmental geochemistry and health special issue. There's a kind of still a gap, research gap exists between what is the mechanism for like causative like agent for our lower respiratory infection work to propose a health risk to the public. And what do the seasonal and weather influence on these spatiotemporal features? We all know, we currently have a project within about medical research, consider within the flu season pattern, with that original from a human or original from ambient air trigger about this season work. So we do, how about this connection interplay between the chemical and microbial agent that are still worsening some of our study in this particular diagram highlight here. Okay, the way forward, anyway, I'm thinking I just highlight from the paper, which actually last year, and how about this biogeochemistry, understanding about this environmental stress, compare within toxicology. We are using a more traditional way from in vitro exposure model, combine effects, but through in vivo collaboration, and getting on this personal exposure finally into the population health issue. So definitely we rely on this kind of epidemiological statistical correlation into the field observation, into final about the realistic approach on the mechanics nature of disease causing effect. Okay, I do not need to read out, but I just want a very quick summary, this take-home message about our connection interplay between the physicochemical and microbial agent in Air PM. I hope I give you a good example to convince you there are many of these further study needed. And we also consider from our point of view, from the source emission, transmission, and the final fate for this both about chemical and biological agent. And we still need about this high resolution monitoring work, particular our earth scientists or geochemists, we are always emphasize this time scale and spatial resolution. So improve our understanding, we can translating scientific evidence into effective policy and control strategy that's contribute overall our society, the world we serve. Okay, I thinking anyways are for one of our paper last year in a critical review environmental science technology, we have using one as this graphic TOC. We have putting on is one world, one earth, and one house. So anyway, I just wanted to give you a few of the reference, both from our group and from other group, particularly if you have interesting for today's topic, this special publication on our society journal, consider on the triad of Air PM pollution, pathogenic bioaerosol, and the lower respiratory infection. So we have mentioned this for this comment article, and also probably about only 3 months ago, we have organized a special issue for urban air pollution and human health, which actually in environmental science and technology, there's over 50 papers there and from 400 submission. So if some of you are interested, it's a good way to read. So, but anyway, there are many other aspects. Some of you, if interesting about the global airborne bacterial community, interaction with Earth's microbiome and anthropogenic activity, this recent public paper in PAS for that. But we do have quite a number of using for the diagram from a series paper from our group or from other group as well. So I believe that's my last line. Thank you very much. I'll be very happy to take any questions.
Thank you very much indeed, Xiang-dong. That was an absolutely fascinating run through some of the work that you've been doing. 2 or 3 things to comment on. Firstly, thank you for starting out with how you got to where you are. That's actually really helpful, I think, for some of the newer members, some of the younger members of where they might want to progress to. So thank you for that. And also, bearing in mind that this has been recorded, the reading list at the end, I think, is also going to be helpful to people to be able to go in and have a look at it. I think you've just given us a talk which very much exemplifies how we are a very broad church within the organisation. We put feet both very much in the geochemistry side and very much in the health side, and you've got one foot in either for that particular talk. So thank you very much indeed for that. I'm just trying to work out if people could, I'm just trying to change my view on this one. So if people could put their hand up to say that they want to ask a question, then that would be helpful. Equally, if you want to stick something into the chat box, that would also be helpful. So I'm presuming there are plenty of questions to come behind this one, because if there aren't, I've got loads of my own. I can't see any hands up yet, but there are quite a few people who've taken off their microphones, so that's suggesting that there are questions to come.
Yeah. Sorry.
No, okay. I actually would like to ask a question. You had a slide early on in there, which was looking at some of the differences across different countries of the effects of particulate matter, and you made the comment about the Middle East, and I can remember working in Kuwait when there was a dust storm came through, yeah. And at that particular time, I was trying to persuade them to reduce some of the outputs that they have from generators, etc. And looked at me and said, "Why are you bothered with this when you can see all of this coming through?" So it's actually quite interesting seeing it from the point of view that you have on there about the level of illness that it causes or doesn't, because you've got dust, but it's pure Saharan sand, which is not going to cause the same level of disease. But as soon as chemistry happens and that Saharan sand moves somewhere else, we have an issue. Would you like to comment on that?
Yeah, Jillian, that's a good point. I thinking you're right, and the dust storm do have a health issue or health impact, that's for sure. Because when you have about this dust storm come over for a large urban area, so you need whatever cover up and stay indoor and we have whatever issue. So that's kind of like I would say isolate like environment event. But for our way, I explained for that diagram we have in a Nature article, comment article, is consider is annual PM2.5 rather than just one event for this dust storm. Yeah. Because if you have about very close to this kind of Sahara Desert type of regions, so the fine PM2.5 have a large proportion for the natural origin. It's kind of like not as a large sand dust, but it's a kind of very fine particle. So that one is, if they are not associated with chemicals, whatever metals or organic, so their toxicity is relatively low. even they have taken a lot of the mass abundance for about this kind of the issue. So that's why we kind of like to analyze the natural origin of the fine particle, because we are not actually on the large sandstone, but we still have this natural origin PM2.5 compared within our anthropogenic source. So that's why these kind of examples to see how about our combustion source of the particle really causing the health issue in the long run. Also consider with a temporary, like acoustic, like a toxicity effect. I hope
Thank you.
explained Jilin for the part. Yeah.
Thank you. I can see that Alekos has his hand up. Alekos, would you like to go, please?
Yes, thank you. Well, Xiang-dong Li, I enjoyed very much your presentation and talk, and I follow some of your research. I'm not an air pollution expert, but I learned a lot today. Now, I'm very particular with definitions.
Yeah.
You use heavy metals and also metalloids, which was more correct. And
Yeah.
you know, the heavy metals, you had arsenic, and arsenic is a metalloid, or it's very good not to use heavy metals, and it's better to use potential hazardous elements. You know, it's something that we should be doing from now on. And also something that we must decide is about the term pollution and contamination, pollutants and contaminants.
Yeah.
Now, pollution means that there is verified harm. Now, the problem is with air pollution, or air contamination, I will say, do we sort of say that we have air pollution when there are exceedances from the guidelines? Good question.
Yeah, of course, and I really appreciate your point and your question. I would say yes, that's true. I just want to using this conventional term, and scientifically, I will actually, as editor for one the recent kind of I would say was kind of this perspective article consider about the compare about trace metal and heavy metal and other common use term we have in kind of whatever environmental chemistry type. I fully agree. So that's kind of is. I just want to using one of this way. It's not in our publication. It's just about daily conversation with our colleague, and I think we are using heavy metal, whatever, for representing a group of elements here. Okay, so that's a very good point. So my second issue is regarding air pollution and air contamination. I'm thinking that's a very good point, but it's very difficult to define because I understand your mean if we have the soil pollution, soil contamination. So the pollution have already been occurred for the whatever impact and environmental fate. But for the air side, I don't think there is a kind of a very much on a clear count consider with pollution and contamination, because I mentioned one the PM2.5 WHO guideline is 5 microgram per cubic meter, but even there's a 4.3, 4. Whatever in certain type of the PM2.5, like the chemical composition I discussed in the slides, can be toxic. So in a word, even if we are say below this 5 microgram per cubic meter is contamination, above is pollution, I don't think that's a clear cut, particularly for the air side, because I highlight the composition, not the total kind of abundance can be a killer, rather than a kind of a issue here. So, for example, if even a lower, but within kind of this pathogen inside can still be a pollution or kind of really causing health effect. So that's why I tending not be that strict. We are called air pollution, air contamination. I thinking particular for away from our geochemical field, and the air pollution always most common use rather than air contamination.
Thank you for that clarification. I hope, Alikos, you're happy with that explanation.
we can go on discussing this. So.
Sure.
off screen, I think. Xiao-Sheng, you have a hand up.
I think the only sort of solution we have in this is with this sort of in the papers, in the introduction, you have to define, let's say, the terms to start with. So the reader will know what you mean by sort of pollution, because I said, I mean, it's verified harm. This was the from the start, and I'm still skeptical about the guidelines, because as Lee knows, they go up and down, and also the particles, as more research, this change. So we have to be, in every paper, I think there should be a definition to start with, so the reader will know what the paper means.
Okay, thank you. That's a good point, Alex.
Xiao-Sheng, would you like to ask your question?
Well, I'm so delighted to see that you have published so many papers. My God, congratulations to them. And anyway, I will not ask questions that's so challenging. Okay, I will ask you a very easy question. You mentioned the high resolution monitoring of those air pollutants. Can you elaborate more about how high the resolution should be, or do you have any comments about the monitoring?
Very good point. I think we need your expertise on GIS as well, because we have been recently got a funding of a large scale air pollution and health research. Is almost I would say about 6 or 7 million pounds of the funding project. So we're going to have 5 years, which actually have about the panel study and the combined cell animal validation and epidemiological study. So what I mean by the high resolution is we cannot just using one high volume PM2.5 to representative exposure for all a small district. So we need a little bit, because everyone have this whatever mobile phone. We want to recruit a certain number of people as our panel. The panel is they're going to consider with very active. They go outdoor for sport, and they can actually in a street canyon, and they actually have this different working environment and home environment. So we want to have a PM monitoring for about this almost 24 hours. So in other words, so the high resolution can be very much on the personal device. So we would really want to understanding is a kind of a different period of exposure and a different type of the personalized exposure before we can, after 6 months, and we're going to have the health check on the urine sample, blood sample. We really analyze some of this kind of really health consequence. So towards about exposure, towards a basic health issue. Yeah. So, but also.
Okay. Yeah. Okay. Yeah. Keep talking. Yeah. Go on.
Yeah. I was thinking another way is how to integrate the spatial difference as well, because like the way is our kind of like a ambient air quality monitoring network never to be on a very high kind of resolution. and particular, for example, in Hong Kong, and although it's a small place, but we only have around about this local environment protection agency is only have around about 11 stations. So they only can basing this 11 station to issue about health warnings on the particular air pollution day. So even they don't have analyzed chemical composition. Even I would say you can see from our study, if PM2.5 around about 35 in one day compared to other 35 in one day, but their results are totally different.
Yeah, well, because there's a huge spatial and temporal heterogeneity.
Yeah.
So it is very challenging to design monitoring and also how you define high resolution. My feeling is that this should be linked to your purpose of your monitoring. Yeah. If your purpose is just to see the overall trend, then you can design a kind of a resolution there. And if your purpose is for management, for government to take actions, then you may think about another resolution. And if your purpose is for remediation, for taking specific site actions, then the monitoring will be at a very, very high resolution. So I just feel because of a heterogeneity there, it's really related to your purpose.
That's true. So for our purpose is, I thinking for 90%, I like the first few slides, you probably remember 90% like population in the world cannot meet this the WHO standard for 5 grams per cubic meter. So I think even in a long run for about 15, 20 years, it cannot meet for about 16, 70%. So how we do it is we wanted to put in another way. We wanted to be on the health kind of like oriented control rather than to reduce the total PM. So if we know about there's less than 5% of total concentration control over about 70% of health outcome, why are we targeting this 5% of the major component to leaving even the PM is still about 25 micrograms per cubic meter fine? So the health risk can reduce from 35 to 25, we reduce half of the premature deaths. So that's exactly what we're touching about the funding agency to give us the money to do this, which we combine the cell and animal and epidemiological study together. First time.
Very good. Anyway, congratulations. Yeah.
It's a big task. It's a big task. I thinking I only can happy for 2 minutes. I know how difficult this task ahead of me. Yeah. Anyway, thank you. Good point. Thank you.
Thank you.
And I was going to start delving quite deeply into COP27 and air quality and reduction, but I don't think we've got that. That's a whole different set. I won't go there. I can see another hand up, however. I'm going to mispronounce your name. I'm really sorry. Tempingozi, would you like to ask your question?
Thank you very much. That's massive work there. Yeah.
Thank you.
Yeah, cheers. I would want to ask, the challenge that we have with the air pollution in terms of the particulate matter in the air and also the microbes.
Yeah.
Which is coming out clearly from the work which you have done over a number of years, which is brilliant. I don't know in the future, are you going to look also into things like nuclear materials in the air, advances in technology, nuclear weapons and this stuff?
That's a very good point. I mean, this kind of considerations, the world is less stable than we thought.
Yeah.
And there are some of the guy who's hanging around can be thrown on any means of whatever the peace we enjoy in the last 70 years.
Yeah,
but anyway,
sure.
We haven't, for our group, for the PM25 and health study, touch the nuclear particles or whatever. But I can, from our early study, which you probably know about this Chernobyl kind of nuclear power station one.
Yeah,
and
sure.
To see, I mean, it's easy to getting signal in the UK, but even in the southern part of China and north part of Vietnam, in the sea sediments, we can really have the signal there.
Ooh.
So in other words, it's totally a global issue.
Yeah,
Rather
sure.
than we thought it's only affecting for European part, but it's not. So in other words, if kind of that's only compared with a nuclear weapons fraud, that's only a relatively small scale. But if that really happened, that would be a human disaster or catastrophe type of issue for as well. I don't have in our scenario, we have never have putting that in our study. I'm not sure how other people can help, and for is a radioactive kind of geology or other type of the issue. But you're right, and this kind of the radioactive material can travel very far away in the air circulation system or in a very fine particle. Yeah, that's kind of like even the word circulate. For Japanese, the nuclear power plant leakage, they can detect it far away in Fiji or other kind of like current. So that's a kind of that's why I still have a bit of doubt. People using nuclear power as a green energy. I'm not sure how our colleague here agree or not. I really have some of my reservation for that. Yeah.
Okay.
Yeah. I mean, although we may actually have some problem reducing the greenhouse gas issues, but they are not green. And you never know, it's once in 200 years or whatever, it can happen. The happen is really a kind of whatever, beyond our easy remediation.
Yeah.
So that's a kind of a really the kind of an issue we need to look at. Yeah.
Thank you.
Yeah, thank you. That's a good point. Good discussion. Yeah.
Absolutely. Okay, I can see that it's actually 3:15. So, and there are no more hands up. So I'd like to say a very, very big thank you to you for that presentation. I thoroughly enjoyed it. And to everybody else who's on here, if you want to go back and have another look at it, the recording will be on the SEGH website. So thank you for now, but also to remind everybody as well that there is a list on the SEGH website of these sessions to come. And there are some really interesting pieces of information, and I can see some clapping hands up on there as well. So exactly, we can't do that in the room, but very much on everybody else's behalf. Thank you very much indeed, and goodbye to everybody.
Thank you, Jillian, and thank you, colleague. I really appreciate it, and it's a great opportunity to meeting online again. I saw quite a number of colleagues, even Professor Fickerman, and then there's Chao Sheng, Alicus, and Andrew, and Oliver, and quite a number of other new friends as well. So I really appreciate and within the SEG family. So you can see I was grew from a young, like kind of PhD student within about SEGH. I really thanks for about this kind of a nice small family. I mean, I was on the ACS service as editor, this kind of the big, giant congregate of this society, but we still value some of your room, home road, where SEGH still provide me and for the early kind of opportunity, both for about this science research and consider about building our academic network. I really thanks for that. So that's why I am putting my way for about this, even the Geochemical Society Club Patterson Award. In acceptance, I mentioned very much clearly the SEGs is my family road. And I would actually say, thank a lot of colleagues and sometimes the friendship over 30 years. And all the best. Thank you very much.
Thank you very much. Thank you.
Thank you, Xiang-dong. Thank you.
Thank you.
Thank you. Okay,
Bye.
all the best.
Bye.
Bye now.
Bye-bye. Bye.
Bye-bye.
Bye.
Bye.
Bye. Bye.
Bye.